Welcome to Robotics 1. In today's class, I'm going to talk about forward and inverse kinematics. I will work out one problem. And if you look at the inverse kinematics problems that we have solved, those problems were very straightforward. So let me reiterate. In forward kinematics, you provide the joint angles theta 1 all the way to could be theta 6, and you find px, py, and pz, which are the end effector positions. This is called as the forward kinematics. In inverse kinematics, you provide px, py, pz, and try to find out thetas, theta 1 all the way to maybe theta 6. Now remember, if you have three unknowns and if you have three knowns, so you have an equation for px, you have an equation for py, you have an equation for pz, and these expressions are maybe f of x, theta 1, theta 2, theta 3, f of y, theta 1, theta 2, theta 3, f of z, theta 1, theta 2, theta 3. You can use a MATLAB solve function to solve these algebraic equations. So you have px, py, pz is given to you, and you have to find out theta 1, theta 2, and theta 3. Now, all this is great as long as there is no gimbal lock. If you have a gimbal lock, this problem cannot be solved, which means if you look at the spherical wrist problem, wherein you supply something like this, I want you to try this spherical wrist and try theta 1 is equal to 30 degrees, theta 2 is equal to 90 degrees, and theta 3 is equal to 45 degrees, and find out px, py, and pz. So this is the forward kinematics. You would have a solution when theta 2 is 90 degrees. Now try to run inverse kinematics and you will see the MATLAB solve function will throw an error. And it throws an error because the system becomes singular. So if you have this condition, theta 2 is equal to 90 degrees, theta 1 and theta 3 as 45 and 30 degrees, you can get some px, py, pz. But when you try to plug this px, this py, and this pz into your inverse kinematic solver, it will not work. That is one practical way you can verify that you have a gimbal lock. The other thing what happens here is in the case of the gimbal lock, two of the revolute joints sort of become perpendicular to each other. Become parallel to each other, something like this. This is the most general specification of gimbal lock. Now I have drawn this slightly differently because I want you to understand this. This joint and this joint, if I rotate this joint by 30 degrees, and if I rotate this joint by minus 30 degrees, overall rotation is 0. Which means you cannot uniquely identify these joint angles that give you the resultant. That is the meaning of gimbal lock, which means two of these joints, they become parallel to each other. So resultant cannot be resolved. And I would encourage you to try this. Look at the code for the spherical wrist. Apply theta is equal to 30 degrees, theta 2 is 90 degrees, theta 3 45 degrees. Any angles are fine as long as the middle angle or the angle in between two joints is 90 degrees. Find Px, Py, Pz and try to find out inverse kinematic solution. The solver will not work. That is because of the gimbal law. Now, in this particular case, I want you to understand that if you do not have a gimbal lock, you have three equations and three unknowns. So you have three equations and three unknowns. So this problem can be solved. Now I want you to understand the MyCobot that you worked on or any other robot that has more degrees of freedom, which means Px is function of theta 1 all the way to theta 6. Py is function of theta 1 all the way to theta 6. Pz is the function of theta 1 all the way up to theta 6. In this case, you have three equations and six unknowns. You cannot solve this system in a closed form unless you make certain assumptions. What it means is you cannot substitute some value of Px, some value of Py, some value of Pz and ask MATLAB or any other software to give you theta values when theta is from theta to theta 6. There is one special case that you can solve in closed form. Otherwise, to solve inverse kinematics, there are numerical algorithms, numerical solvers. And numerical solvers, they again are one or the other technique using some type of an optimization, forward, backward propagation, and some type of an approximation. So what it means is for 3 degree of freedom robots, you can find the IK solution if there is no gimbal lock. When you have more than 3 degree of freedom robots, only in special cases you can find out the inverse kinematic solution. Otherwise, most of the time we are going to use some type of numerical solver, and there are two famous numerical solvers, we'll talk about those, that are used to find inverse kinematics solution. That being said, what I want to do today is I want to take one last problem for forward and inverse kinematics, and then actually I would take you to how these problems are solved using a MATLAB or some other solver. So let me take an example because this is one of the classic robots. So this robot is you have a revolute joint, then you have a another revolute joint. So this is R perpendicular to R. And at the end, what you have is you have a prismatic joint. You have a prismatic joint. So this joint is prismatic. This is P. This joint is revolute. This joint is revolute. So this, if you think about it, in this robot configuration, I'm gonna apply the coordinate frames. I'm gonna apply the coordinate frames. The joint direction has to be Z. So this is gonna be my Z0. I will call this as Z1. I would call this as Z2. And at the end effector, this is my end effector, I would call this as Z3. So first step is to identify all Z's. Then this would be my X0. Again, there is no coordinate system before Z0. So it doesn't matter which direction you draw X0. At the end, we need to complete the triad using the right hand coordinate system. So my Y0 is going to go in this direction. This is my Y0. So this is my Z0. This is my Z0. This is my Y0. This is my X0. Remember the rules. First rule, Z axis through joint. Second rule, XN must intersect XN must intersect Zn and Zn minus 1. And last thing, that we need to have a triad. So RH, right hand coordinate system. So this is what we are looking at. Now what we are going to do is, tell me, where should the X be? Should my X1 be like this, or should my X1 be going up? The way I have drawn, this is going to be my X1. So because when I have X1, you can see the axes, they extend infinitely. So my Z0 intersect with X1 and X1 already intersects with Z1. Curl your fingers and you have your Z, you have your X, and this is going to be my Y1. Now let's go to Z2. But before we go to Z2, I want you to ask yourself a question, like where should I draw my X2? Vertical, horizontal? So if I draw my X2 horizontal, then please understand it's going to be parallel to Z1. If I draw my X1 vertical, still it's going to be parallel to Z1. Shift. Oh, yeah. Yeah, just think about it. Where would you draw your X1? X2. Okay, let me draw this again. If I draw X2 like this, can you see, if you see from front, my X2 is going to be parallel to Z1. If I draw my X2 in this direction, do you agree with me? Still, it's going to be parallel to Z1, which means rule number 2 is not going to get satisfied, no matter what I do. Everyone understood this? So this is an exception to rule. So when I have an exception to the rule, I'm going to say, I'm going to assume that X2 to be like this. If my X2 is like this, then my Y2 will be like this. So please understand, this coordinate frame does not satisfy the rule, which means we have to translate it back. You remember, we have to translate it back. But let's go on further. And right now we have the last coordinate frame. I'm going to use the same coordinates. This is Z3. I'm going to have this as Y3. And this will be X3. Are you with me? Any questions about the coordinate system? So please note here, rule 2 not satisfied. But that's okay because we cannot satisfy that rule anyways. Now, let me identify the joint angles. So this is going to be my theta 1. This is going to be my theta 2. And now please understand, I don't have a rotation. I have a translation. So typically the translations are identified as D. So this will be my D3. So this talks about the translation. And then I have these distances. These are the joint distances. I'm going to call this as A1. I'm going to call this as A2. And there are different ways of doing this. If the actuator does not have its own length, then you don't have to basically specify any distance. If it has its own length, then you can specify some non-zero value there, which means you can have A3 here, or it doesn't have to be. But this is the setup. And what I'm going to do is I'm going to start with 0R1. This is the rotation about Z. So it's going to be cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Don't forget the projection matrix. The projection matrix is x0, y0, z0, x1, y1, z1. X0 coincides is note x0 is in the same direction as x1 and it's parallel. So x1 0 0, y1 is in the same direction as z0 and z1 is minus y0. Are you with me? Any question about the projection matrix? Now you need to perform this multiplication. First row, first column, cosine theta 1, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, first row, first column, 1, 0. So this is my first rotation transformation. And I'm gonna write my homogeneous transformation here, 0h1. 0h1 would include 0r1, cosine theta 1, 0 sine theta 1, sine theta 1, 0 minus cosine theta 1, 0, 1, 0. Here 0, 0, 0, 1. And now the distance is here. Once again, in the homogeneous transformation, the first row, fourth column is the distance between the previous frame and the current frame in the coordinates of the previous frame. The distance between x1 and x0 along x0, that is 0. Distance between y1 and y0 around about y0, 0. Distance between z0, z1 and z0 in the coordinate frame of z0, which is a1. Are you with me? Everyone understood? Next part is now I need to go to the second frame, but the problem here is the rules are not satisfied. If the rules are not satisfied, then what I need to do is I need to translate the frame from here to here. When I translate the frame, I get, let me use a different color, I get this frame. So this is going to be my X3. So X2, this is going to be my Z2, and this is going to be my Y2. So once again, I will draw this coordinate frame. So you have this coordinate frame. And what I need to do is, I need to go with again 1 R2. 1 R2 is cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. And then I'm gonna have X1, Y1, Z1, X2, Y2, Z2. And just for clarity, I will redraw that coordinate frame here. So this is my X1, this is my Z1, and this is my Y1. And after I translated, I get this guy, which is my Z2. I get this guy, this is my X2. And I get this guy, this is my Y2. Are you with me? So I translated the frame. Now in this current configuration, rule number 2 is satisfied. Do you agree with me? My X2 intersects with Z2 and X2 also intersects Z1. Are you with me? So X2 is in the same direction as Y1. Y2 is in the same direction as Z1. And Z2 is in the same direction as X1. Are you okay with the projection matrix that I have shown there? Now, when I perform this multiplication, I get this matrix minus sine theta 2, 0, first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, 0, 1, 0. Are you with me? Now comes the homogeneous transformation for 1H2. I will write minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0. And here there will be 0, 0, 0. Here there will be 1. And please note, in the configuration shown, X1, Y1, Z1, they intersect with X2, Y2, Z2. So they are on top of each other, which means there is no relative distance between these two coordinate frames. Everyone understood this? So you have 0, 0, 0. Are you with me so far? Now the next question that comes is, and this is an important question. I want you to understand this. Next question that comes is, what happens when you have 2R3? What happens when you have 2r3. And again, there are two ways of doing this. First and foremost, understand that 2r3 indicates the rotation between these two frames. But there is no revolute joint in between. So there is no rotation. So which means what you can do is write 1 0 0 0 1 0 0 0 1. Why is that? Because there is no rotation, there is no hinge joint. Everyone understood this? Alternatively, if you don't want to do this, you can blindly follow the procedure. Cosine theta minus sine theta 0, sine theta, so sine theta 3, cosine theta 3, cosine theta 3, 0, 0, 0, 1, and substitute theta 3 is equal to 0. And still what you get is you are gonna get this identity matrix. Do you agree with me? 1, 0, 0, 0, 1, 0, 0, 0, 1. However, you would still have the projection matrix. Projection matrix indicates the projection matrix indicates the relative orientation of the frames. So even though you may not have a rotational joint, but these frames could be oriented in different way. So for this problem, I would have x3, y3, z3, x2, y2, z2, and check this out. My x3 is aligned with x2, my y3 is aligned with y2, and my z3 is aligned with z2. Do you agree with me? So I would just write 1 0 0 0 1 0 0 0 1. So which means all said and done, my final rotation matrix is going to be 1 0 0 0 1 0 0 0 1. Now I need to formulate the homogeneous transformation, and to formulate homogeneous transformation 2H3, I would repeat the relative transformations. And then I would have 0 0 0, and then I would have 1 here. Now I want you to think about this, the way this problem is set up, and tell me the relative distances between the frame 3 and the frame 2. Again, in this homogeneous transformation, here I'm looking at the distance between the frame 3 and frame 2 in the coordinate frame of frame 2 about x. The y distance between frame 3 and frame 2 along y2. And last one, the distance between 3 and 2 in z in the direction of z2. Are you with me so far? So tell me what would come here.
0 0 0 3 plus 3.
Correct. So it will be 0 0 0 0, and last one would be a3 plus no a2 plus d3. Are you with me? Yeah. How the rotation of theta 2? Okay, would the theta, all right. What I'm gonna do is, if you have a robot in a 3 dimension, here is what I would do. What I want you to do is, let me draw this robot. Okay. Let me draw this robot. And what I have here is I have a prismatic joint. Now, what I want you to do is, I want you to look at this robot once in front view and other in top view. So imagine yourself standing here. You look at this robot. Let me set up the coordinate frame. Same coordinate frame. Z0, X0, and Y0. This distance is A1. This angle is theta1. This angle is theta2. And this extension is D3. Are you with me so far? I'm not plotting, I'm not drawing any other coordinate frames. So I want you to think about this. Now, if you look from in the front view, this is what you are gonna see. You will see in front view, you will see these two axes. You will see X0 and you will see Z0. Do you agree with me? And what you would see in X0, in here, you would see that the first revolute joint will be at 0, 0. Second revolute joint would be at distance A1. This would be the distance A1. And the second revolute joint would be, if it is 0, it will be like this. If it is non-zero, then maybe it would be like this. Do you agree with me? So this angle, do you agree with me? This is theta 2. This angle is theta 2. And if you have this cylinder, that cylinder can extend. So let me show you the distances between these two. This is A2, E2. So this distance is going to be A2. This is going to be fixed because the cylinder is here. And this distance is going to be D3. Do you agree with me? Now what I want is, I want two distances. So this is my end effector. This is my end effector. I can use the right angle triangles. I can use the right angle triangles and find this distance as A2 plus D3 sine theta 2. Do you agree with me? And I can find this distance as A2 plus D3 cosine theta 2. Do you agree with me? Now please understand, D3 can extend or retract. Theta can change, but this relationship is not going to change. Do you agree with me? So which means, now understand the second case. Look from top. Look from top. When you look from top, now you would notice that you have Y naught visible and X naught visible. You have Y naught visible and X naught visible. You agree with me? Now, but whatever you do, the lever arm that you are going to see is nothing but A2 plus D3 cosine theta 2. You agree with me? Once you look from top, you are going to see the projection. This projection, you are going to just see this projection. This projection is going to be This is extremely important. I want you to understand. When your theta 1 is 0, when your theta 1 is 0, you would see this projection something like this, which would be A2 plus D3 cosine theta 2. Do you agree with me? But if your theta 2 changes, then what's going to happen is this is going to sweep, which means if your theta 1 is somewhere over here, if your theta 1 is somewhere over here, then please note that your distance here is going to be A2 plus D3 cosine theta 2 multiplied by cosine theta 1. Do you agree with me? And this distance is going to be A2 plus D3 cosine theta 1 sine theta, no, cosine theta 2 sine theta 1. Do you agree with me? Now please understand, when theta 1 is equal to 0, this would be your total distance, A2 plus D3 cosine theta 2. When theta 1 is equal to 90 degrees, your total distance is going to be A2 plus D3 cosine theta 2. In between, you have this right angle triangle, which means just by looking at the front view and top view, I can write the expression in closed form for Px, Py, and Pz. Remember, Px, Py, Pz are the distances from the zeroth frame or the inertial frame. So I want to find out where my end effector is with respect to x0, y0, and z0. Everyone understood this? So I can write my Px as A3 plus D3 cosine theta 2 cosine theta 1. My Py as A2, oh A2, this is A2, sorry. A2, A2, A2 plus D3. A2 plus D3 cosine A2 plus D3 cosine theta 2 sine theta 1. And last but not least, in z direction, it would be A1. A1 is fixed, right? Plus A2 plus D3 sine theta 2. Are you with me so far? This is your forward kinematics. We don't have to do the matrix multiplication, but we found the answer. Let me tell you, if you follow the process that we have followed here, and I would encourage you to try that. If you say 0h3, 0h1, 1h2, 2h3, you are gonna get a big matrix, and you would see here you are gonna get Px, Py, Pz, and you are gonna get 1 here, 0, 0, 0 here. One last thing. We have derived this expression for forward kinematics, but we really don't know anything about the orientation of the end effector. We don't know how that end effector is oriented or rotated. Now, once you perform this 0h3, this rotation 0r3 is given to you. So this 0r3 matrix, and it is extremely important, 0r3 shows orientation orientation of end effector with respect to 0th frame. And the 0th frame is x0, y0, z0. Now, for us, it's difficult to visualize because please understand, after you perform all this multiplication, theta 1, theta 2, all those angles will be inside this 0R3. So you are going to get a 3 by 3 matrix. This is called as the rotation matrix. This is difficult to visualize. The easier way to visualize is we can convert these rotations into Euler angles. In terms of Euler angles, we talked about Euler angles. You have roll, pitch, and yaw. So I want to talk about this. So it's difficult. So what we do is to visualize rotation matrix is converted to Euler angles. And Euler angles are nothing but the rotations about the axes. So for example, if you have this axis, you have this z, you have this x, and say you have this y. So x0, y0, and z0. Euler angles are nothing but successive rotations about these axes. Euler angles are nothing but successive rotations about these axes. And I want to actually show you this example, and it's actually extremely important. Think about it. So if I perform rotation about one axis followed by other axis, these rotations are not commutative, which means if I change the sequence of operation, the final orientation is going to be different. Once again, first rotation, second rotation. Now, instead of doing that, I do the second rotation first, and then to change the rotation, the final orientation is different. Everyone understood this? Now, this requires a little bit of more discussion. I don't want, okay, let's see. I will explain it to you in terms in pure math. So Euler angle, Euler rotations are not commutative. Now what this means is 0R1 and 1R2. If I have these two rotations, if I multiply these two rotations in a different sequence, say 1R2 and multiplied by 0R1, my final result is not going to be the same. Rotations are not commutative. Now the problem here is these rotations are called as finite rotations. So finite rotations are not commutative, but infinitesimal rotations, extremely small rotations are commutative. So, but infinite means small, decimally small rotations are commutative. Now, what does it mean? basically, there's a very nice mathematical derivation for this. What it means, if I have a big rotation, then the rotations are not commutative, which means I cannot change the sequence of rotations. But if I have extremely small rotations, then the rotation sequence can be changed. And that is the trick that is used in solving these kinematic problems. So, example, aircraft. Now I have these big rotations. Clearly, the orientation is different. So I now the aircraft is going to look differently if I change the sequence. But as soon as I change the sequence very, very small, the final orientation will not make a big difference. And there is a very nice mathematical proof for this. I don't have time to derive that, but I will try to explain this in next class. Yeah.
What angle could be classified as?
Yeah, small angle is like fraction of a degree. So about 0.1 to 0.2 degrees, the rotations can be considered. Actually, it's a very good question, and unfortunately, this question is not answered properly in the textbook. So I would like to discuss this. So please ask me this question in next class, and I will actually derive what it means by small rotations are commutative and large rotations are not. So I need to basically derive that mathematical expression so that you will understand, because this is extremely important. So Euler angles are sequential orientations about these axes. First orientation is about z, which is called as yaw. Second orientation is about x, which is called as pitch. And the last orientation is about y, which is called as roll. So we actually go with this sequence. Now please note, first rotation was z, second rotation was x, and last rotation was y. There are 12 combinations of Euler angles, which means, remember, we can change the sequence. You can go zxy, you can go yxz, you can go zyx, and so on. There are 12 combinations possible. But from engineering point of view, this is the most common Euler angle representation that is being used. So what we do is, once we get this matrix, we use the MATLAB command. So that is rotation matrix to Euler. And once you specify this command, it will take the rotation matrix, 3x3 rotation matrix, and will give you roll, pitch, and yaw angles. We don't do that by hand. We can do that by hand, but the best way to solve this problem is using MATLAB.
The commands like a function.
Yeah, it's a MATLAB command, which is called as ROT to M, ROT M to UL, ROT M to EUL. You can go to MATLAB and look at the help. If you have Euler angles, and if you want to convert those Euler angles into rotation matrices, the command is EUL to ROTM. This will take Euler angles, roll, pitch, yaw. So you'll supply roll, pitch, yaw, and it will give you a rotation matrix, 3x3 rotation matrix. Here you will supply a 3x3 rotation matrix, and then it will give you roll, pitch, and yaw. Okay. Now, as far as we are concerned, we can work in rotation matrices, we can work in quaternions, you can work in direction cosine matrices, it doesn't matter. But when it comes to actual plotting, we can't plot quaternions. We can't plot Euler parameters. We can only plot rotation matrices. So when it comes to plotting, or when it comes for visualization, the angles are expressed in Euler angles and the robot configuration is drawn. Everyone understood this? But this is an important comment. Small rotations are commutative, large rotations are not. So in the next class, I will show you with matrix manipulations. Why is that? Okay, now the next part is I want to talk about how do you solve inverse kinematics for 6 DOF robots. Now I hope everyone understood. Once we find this H01, 0H1, 1H2, 2H3, program that in MATLAB, perform the multiplication, and you would get Px, Py, Pz. Everyone understood that, right? I don't have to work out the problem, but you can check. Now here comes the problem. If you have a robot that has more than 3 degree of freedom, and it can be anything, how do you solve for inverse kinematics? Now let's identify what's happening here. Whenever you are going to solve for 6 degree of freedom robot, the inverse kinematics problem will be, you would be given Px, you would be given Py, you would be given Pz, which means you would be given end effector position. So this is end effector position. And you would be given end effector orientation. So you would be given roll, pitch, yaw, which is the end effector orientation. And now you have 6 unknowns. You can find out theta 1 to theta 6. Example, the MyCobot that you have looked at in the lab, it's a 6 degree of freedom robot. If you want to solve the inverse kinematics of that robot, you need to specify the end effector position and end effector orientation with respect to the 0th coordinate frame. You need to know where the robot is and what angles the end effector is oriented. So you need to have Px, Py, Pz and roll, pitch and yaw. Everyone understood this? However, you cannot directly use MATLAB to solve this type of a problem. Because if you try to solve an inverse kinematics problem, when you supply Px, Py, Pz, roll, pitch, yaw in just one code, most likely MATLAB will not work. It will go into infinite loop or it will throw an error. So how do you solve this inverse kinematics problem for 6 degree of freedom robot? Always, first step is to solve forward kinematics problem. Solve forward problem. So you will do 0h6, which is you will find 0h1, you will multiply by 1h2, you will multiply by 2h3, 3h4, 4h5, and 5h6. And once you are done with this, you are gonna get this big matrix. Are you with me? This will be 0R6 and this will be Px, Py, Pz. 0, 0, 0 and 1. Everyone understood this? The only way you can find a meaningful closed form solution is to separate this problem into a manipulator problem and a spherical wrist. What it means is you would separate out the 6 degree of freedom robot, theta 1, theta 2, theta 3 as a manipulator problem, and theta 4, theta 5 and theta 6 as the wrist problem. Which means what you would say is extremely important. Theta 1, theta 2 and theta 3 are responsible for getting Px, Py and Pz, and theta 4, theta 5 and theta 6 are responsible to get 0 or 6. Are you with me? So you have 6 degrees of freedom robot. There are 6 angles. You cannot directly solve the inverse kinematics problem in a closed form like expressions. So we split the problem into a manipulator problem and the wrist problem. Manipulator, which means the first 3 joints are responsible for attaining the end effector position, and last 3 joints are responsible for achieving end effector orientation. That is the assumption we have to make to solve inverse kinematics problem. So how would we do it? Well, the first part is very simple. You have Px, you have Py, you have Pz. You have Px, you have Py, Pz. What I would do is, I would find 0h3, which is 0h1, 1h2, and 2h3. And I would get this big homogeneous transformation matrix with 0R3, and there will be the expression for Px. I'm going to call this Fx, Fy, Fz. And since we only have 3 angles, Fx, Fy, Fz will be dependent on theta 1, theta 2, and theta 3. So I'm going to write down Px, Py, Pz, which we have over here, which I'm going to write that down as f of x, theta 1, theta 2, theta 3, f of y, theta 1, theta 2, theta 3, f of z, theta 1, theta 2, theta 3. Please note, I got these by solving forward problem for theta 1, theta 2, and theta 3. Everyone understood this? This expression can be solved. You can substitute some value of Px, substitute some value of Py, some value of Pz, and find out theta 1, theta 2, and theta 3. So at the end of this solution, now you know theta 1, theta 2, and theta 3. Do you agree with me? Now understand, you have 0R3 over here. This 0R3 is also a function of theta 1, theta 2, and theta 3. Do you agree with me? This is the function of theta 1, theta 2, and theta 3. You would substitute these known values of theta 1, theta 2, and theta 3 and find out the actual answer for theta 1 R0 R3. So you will actually get numbers here. So that this will be actual some numbers. And it would be like 0, 0.1, 0.2, whatever that it may be. But if you look in homogeneous transformation, 0R3 is expressed as the function of theta 1, theta 2, and theta 3. Here, you would substitute theta 1, theta 2, theta 3 and get this matrix in numbers. Everyone understood this? Now, here comes the last part. In the last part, you have roll, pitch, and yaw of the end effector. Yaw of the end effector. This is known. So you would use the MATLAB command EUL to ROTM and you will substitute the roll, pitch, yaw and find out this 3x3 matrix in numbers. Roll value is given, maybe 30 degrees. Pitch value is given, 45 degrees. Yaw value is given, 60 degrees. So you can use this command Euler EUL to ROTM and you will get this 3x3 matrix. So this guy is completely known. This guy is completely known. So you have numbers here, right? Are you with me? Now the last thing that you will do is, let's write down 0R6, which is this guy, is equal to 0R3, which is this guy, multiplied by 3R6. You agree with me? And this 3R, so this is known. This guy is known, but only unknowns are in this guy, theta 3, theta 4, theta 5, and theta 6. So unknowns are theta 4, theta 5, and theta 6. Are you with me? So what you would do now is you would invert this matrix. So you have this matrix 0R6, which is known in terms of values. This is completely known. Invert this matrix 0R3. This is also a numbers. It's full of numbers. So this guy is known. So now whatever product that you are gonna get, you would equate it to 3R6. Now some of you may ask me, how do I solve this matrix equation? Solving matrix equation is very easy because now what you do is you do term by term comparison, which means you have a matrix here that is in form of numbers and you have a matrix here which is the product of cosine theta 4, cosine theta 5, cosine theta 6, cosine theta 4, cosine theta 5, cosine theta 6. So every term in this 3x3 matrix is a product of theta 4, theta 5, and theta 6. Do you agree with me? Which means you have 9 equations to find out only 3 unknowns. And since it's an orthonormal matrix, no matter whatever equations you use, you will be able to find out the same theta 4, theta 5, theta 6. Are you with me? And make sure you understand this very well, because this is what I have asked you in your next assignment. I have asked you to solve the inverse kinematics problem for the Fanuc robot. Fanuc robot, if you want to solve the inverse kinematics problem for the Fanuc robot, first you will solve the forward kinematics problem. After you solve the forward kinematics problem, you would get these expressions. Then you would, when you want to solve the inverse kinematics problem, you would make an assumption that the end effector position will be reached by the manipulator end effector orientation will be reached by the rest, which means last three joints. You will separate out those two parts. First, equate the manipulator kinematics, find out theta 1, theta 2, theta 3. From those theta 1, theta 2, and theta 3, you will find out 0 R3. And then what you would do is your final manipulator orientations, which will be typically in roll, pitch, and yaw. You will convert that into a rotation matrix. This matrix is known, so you would have to invert this guy. And actually, I made a mistake here. This should not, I shouldn't invert it like this. I should be inverting this like this. 0 R3. Fine, invert. Yeah, so only then this will become an identity matrix. I cannot invert, I should not post multiply, I need to pre-multiply. So please note, this is a mistake that I made. So I need to invert that matrix, multiply with 0 R6, and then finally do a term by term comparison and find theta 4, theta 5, theta 6. Yeah,
The first three angles.
for to find first three angles, you assume that the end effector position Px, Py, Pz that is given to you is achieved by the manipulator. So theta 1, theta 2, and theta 3 will determine what the Px, Py, Pz is going to be. And the last three joints will determine the orientation of the end effector. Everyone understood this?
Sir, but the base joint can also contribute to the PX, PY, PZ, right?
Correct. So
How are we assuming this? Like, if you are assuming this, we are only taking the motor 3 to the end effector point.
correct. Inverse kinematic can have multiple solutions. So we are finding one such solution. Now, is this done in actual practice? No. Unless you have a very simple robot that actually truly is a spherical wrist at the end, you cannot use this technique. But I want you to use this technique for the assignment. So this is how you would find the inverse kinematics problem. But when you look at the real life robots, including the Fanuc robot or the Puma robot or the UR5, UR10 universal robots, you use numerical techniques. Numerical techniques are at the end some type of trial and error and optimization back and forth. And I'm going to show you how the real life robot problems are solved. But before I go there, let me be absolutely clear. In your assignment, I want you to find the inverse kinematic solution from this technique. Everyone understood this? Okay. Now, what I'm going to do is, I want you to go to MATLAB. I want you to go to MATLAB. I want to share the screen. Please go to MATLAB. Open MATLAB. Just need to make sure entire screen should be visible. Share. Okay. Go to MATLAB. What I'm going to do is a lot more interesting and lot more fun. So if you have MATLAB, please open it. Because this will save you a lot of headaches in your assignment and in your labs. Go to apps. Pull down all the apps. Correct. Because I showed you in the lab. Now go to robotics and autonomous system toolbox. And there is this inverse kinematics designer. Click on this app. So click on the inverse kinematics designer app, which is in robotics and autonomous systems toolbox. And that app will open. This app is opening.
What is it called again?
Inverse. So go to applications.
First kinematics.
Inverse kinematics designer. Yeah, if you don't have it, you will have to download it. And this is what it should open. Are you with me? If you don't have it installed, you will have to go to add-ons, add robotics and autonomous systems toolbox. So it will actually install 4 toolboxes: inverse kinematics app, ROS driver, ROS linker, so all that stuff. So, okay. Everyone pay attention. This is going to be extremely useful for your assignment and even for your lab. Go to new session, click. And when you click new session, you get this rigid body tree. MATLAB has created Universal Design Robot Descriptor Language, URDF. So you can actually so what you can do is, if you have a robot in the SolidWorks or Autodesk Fusion, you can create a URDF, which is the Universal Descriptor Language for robots. Import that URDF inside MATLAB or inside Gazebo or inside ROS, and you can analyze that robot. Example, go to this and you will see there are at least 15 to 20 robots that are already built in, starting from ABB, KUKA, Atlas, and remember this is the LRMate 200 IB. So click this robot, click OK, and that robot will get loaded inside your environment, or they call it scene. So this robot will get installed in your scene.
So just select that robot and click OK.
Yeah.
Okay.
And you have the robot in the scene. Now let's go step by step. Please note that that robot is located, the 0th frame is located at 0, 0, 0. The base link, this is the base. Now, please note this robot does not have any inertia. So that's why the inertia tensor is 0. But you can actually get the inertia properties and populate this inertia tensor. So you can populate its IXX, IYY, IZZ, and all cross products. That we will do when we go to robot dynamics. We are doing kinematics, which means for the time being, our robots are massless. So don't have to worry about inertia. Now, next thing is I want to walk you through this. Go to base. Now, as soon as you click link, can you see there is this joint 1? Joint 1 is Revolute joint. You have the parent transformation, child transformation, and that we will discuss later. But this also talks about the joint limit, which means the first joint can go plus to minus 160 degrees. Everyone understood this?
Yes, sir.
Then you go to the second joint, third joint, fourth joint, fifth joint, sixth joint. It will give you to the flange and it will get you to the tool. Now this toolbox is extremely powerful. You can actually create collisions, you can detect collisions, you can create bounding boxes, you can do pick and place, you can do a lot of stuff here. But for today's problem, if you want to solve the inverse kinematics problem, what you do is, notice you have this solver setting. This is the inverse kinematic solver that is built inside the MATLAB. There are only two standard solvers that are used. One is the gradient projection and second one is LM. And there are papers on how these solvers are worked out, how they are stabilized, just like numerical integration. These are numerical solvers. So these are two solvers. And what you do is, if you want to do inverse kinematics, what is inverse kinematics? Provide end effector position and orientation and get the joint angles. End effector position and orientation, get the joint angles. Go to this marker pose constraint. End effector body is tool. Can you see that? And you have Px, Py, Pz, and you have the Euler roll, pitch, and yaw. Euler about Z is yaw. Euler about Y is roll, and Euler about X is pitch. Everyone understood this? So substitute values, say 0.6, 0.5, and then say apply. And then can you see that robot will change the orientation, and you can go through the joints and you will find out the angles. So joint 1, joint 2, joint 3, joint 4. So it will solve the inverse kinematics problem for you. You are welcome to basically change the solver. You can change the different solver. And then you can try to find out the inverse kinematics. In certain cases, one solver works better than the other. But I would strongly encourage you to go to Inverse Kinematics Designer Help. Inverse Kinematic Designer Help in MATLAB. It will describe all the functions that you have available. With that, I'll stop here.